projects. In this video, we are going to explain about the project title, An Intelligent Approach to Improving the Performance of Threat Detection in IoT. Introduction. The project acknowledges the widespread use of IoT, Internet of Things, devices in various aspects of our lives and emphasizes the vulnerabilities these systems face regarding security threats. It sets the stage by highlighting the significance of IoT in our everyday routines while drawing attention to potential risk. The project specifically focuses on security vulnerabilities in the edge network areas of IoT systems. These weaknesses involve potential threats such as unauthorized access to sensors or the risk of denial of service (DOS) attacks. By pinpointing these vulnerabilities, the project aims to raise awareness about the possible consequences that can arise from such security gaps. The project suggests a solution in the form of a model. This model is designed to predict distributed denial of service (DDoS) attacks in IoT systems by employing a combination of machine learning algorithms and principal component analysis technique. Its purpose is to identify and forecast potential DDoS attacks before they occur. The project mentions the utilization of two specific datasets, namely CIC-IDS 2017 and CIC-IDS 2018. These datasets are employed to assess and evaluate the performance of the proposed model. By using real or simulated data from these sources, researchers can gauge how effectively their model detects or predicts threat. The primary aim of the proposed model is twofold: to enhance the efficiency of threat detection in IoT systems and to reduce the time required for training the model. Essentially, it seeks to improve the accuracy and speed of identifying potential security risks within IoT networks. Objective of the project is: the primary goal of this project is to enhance the effectiveness of identifying potential threats within IoT systems. It plans to achieve this by leveraging a combination of machine learning algorithms and principal component analysis technique. By amalgamating these methodologies, the project aims to create a more robust and accurate system for detecting security threats. Specifically, the project concentrates on training and predicting distributed denial of service (DDoS) attacks within IoT systems. The proposed model intends to be capable of learning patterns and behaviors indicative of these types of cyber attacks. Prediction here means being able to identify and warn about potential DDoS threats before they happen. Data dimensionality reduction is a key aspect addressed in the project. Principal component analysis (PCA) techniques are used to decrease the complexity of the data by transforming it into a more manageable form. By reducing the number of dimensions while preserving important information, PCA aids in improving the efficiency and effectiveness of machine learning algorithms. The project employs two particular datasets, CIC-IDS 2017 and CIC-IDS 2018, for evaluating the proposed model. These datasets likely contain relevant information regarding IoT system behavior and potential attack patterns. They serve as benchmarks to assess the accuracy and performance of the model in identifying and predicting threats. The overarching aim of the project is to create an intelligent and efficient methodology for enhancing threat detection capabilities within IoT systems. The end goal is not just to detect threats more effectively, but also to improve the efficiency of training the system. By achieving this objective, the project aims to significantly enhance the security posture of IoT networks. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first one is importing the packages. This step involves importing necessary libraries or packages in the chosen programming language, like Python, that provide functionalities required for data analysis, visualization, machine learning, and data processing. Commonly used packages include Pandas for data manipulation, Matplotlib and Seaborn for visualization, scikit-learn for machine learning algorithms, and other relevant libraries. Exploring the dataset. This involves loading and examining the datasets used in the project, namely CIC IDS 2018 and CIC IDS 2017. Exploratory data analysis EDA techniques are applied here to understand the structure, features, and characteristics of the data. This step includes checking for missing values, understanding data types, summary statistics, and initial visualization to gain insights into the data. Data processing. This stage involves preparing the data for analysis. Steps like removing duplicate entries to ensure data cleanliness, handling missing values, if any, and performing data cleaning operations such as dropping irrelevant columns or rows fall under this module. Data visualization using Seaborn and Matplotlib. Visualizations are created using Seaborn and Matplotlib libraries to better understand the data distribution, patterns, correlation, and relationship between variables. This step helps in identifying trends or patterns that will be useful in modeling and feature selection. Label encoding. In machine learning, categorical data often needs to be converted into numerical form for algorithms to process. Label encoding is a technique used to convert categorical strings into numerical integers. Feature selection. This step involves selecting the most relevant features columns from the dataset that contribute significantly to predicting the target variable. Techniques like correlation analysis or mutual information will be used to identify the relationship between features and the target variable. Appending selected features to X and target column to Y. After feature selection, the chosen features are appended to the variable X, which represent the input data, and the target variable or column is assigned to Y, which represent the output or prediction target. Splitting the data to train and test. The dataset is divided into two parts, a training set used to train the machine learning model and a separate test set to evaluate its performance. This step ensures the model is trained on one portion of the data and tested on another to assess its generalization capability. Building the model. This involves selecting an appropriate machine learning algorithm, training the model using the training data, and fine-tuning its parameters to achieve optimal performance in predicting or detecting threats within IoT systems based on the selected features. Training the model involves using the selected machine learning algorithm on the training data to create a trained model. The model learns patterns, relationships, and features from the training data to predict threat detection in IoT systems. Flask framework with SQLite for sign up and sign in. A Python web framework used to build web applications. It's employed here to create web endpoints and manage interactions between the front end and back end. A lightweight database used to manage user authentication, sign up and sign in functionalities within the web application built using Flask. User gives input. Through the front end of the web application, users can input relevant data or information related to IoT systems and potential threats. The given input is pre-processed. The user provided input is pre-processed, similar to the earlier steps, to ensure it's in a suitable format for the trained model to make predictions. Data undergo encoding, cleaning, or feature engineering to match the format expected by the model. The trained model is used for predicting the result. The pre-processed user input is fed into the trained model to predict the likelihood or presence of threats in the IoT system based on the learned patterns. Final outcome is displayed through front end. The prediction result or threat assessment from the model is displayed back to the user through the front end of the web application. This could involve displaying threat levels, recommendations, or any other relevant information to the user. Algorithms used to implement this project, we have utilized the following algorithms with PCA and without PCA. The first algorithm used in the project is random forest. Random forest with PCA. Random forest constructs multiple decision trees using bootstrapped samples and a subset of features. PCA before applying random forest reduces the number of dimensions while retaining the most relevant information. This reduction can improve training speed, decrease memory usage, and mitigate overfitting by focusing on the principal components that explain the most variance in the data. Random forest without PCA. In the absence of PCA, random forest operates directly on the original feature space. It does not require more computational resources and time, especially with a large number of features, which leads to increased model complexity and potential overfitting. Decision tree with PCA. Decision trees recursively split data based on features. When preceded by PCA, decision trees work on a reduced feature space, which simplified the tree structure, making it less prone to overfitting and potentially improving interpretability. Decision tree without PCA. Without PCA, decision trees build the tree structure based on the original feature set. With many features, it creates complex trees that capture noise and lead to overfitting. Extra tree with PCA. Extremely randomized trees create random decision trees using random splits on random subsets of features. With PCA, extra trees benefit similarly to random forest by operating on a reduced feature space, potentially improving efficiency and reducing the risk of overfitting. Extra tree without PCA. Extra trees, when used without PCA, operate directly on the original features. This leads to longer training times and a higher risk of overfitting, especially when dealing with high dimensional data. Navy base with PCA. Navy base assumes feature independence. PCA does not significantly affect Navy base performance but can reduce noise and computational complexity in high dimensional data sets by compressing the feature space. Navy base without PCA. Navy base operates directly on the original data, making its predictions based on features conditional independence assumption. It does not efficiently handle high dimensional data or reduce computational complexity. SVM support vector machine with PCA. SVM aims to find an optimal hyperplane separating classes. PCA aids SVM by reducing the number of features, allowing it to work in a reduced feature space and potentially improving generalization and computational efficiency. SVM without PCA. SVM without PCA operates on the original feature space with a high number of features. SVM might be computationally demanding and prone to overfitting due to the curse of dimensionality. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. With PCA, ensemble methods benefit from PCA by utilizing predictions from models trained on a reduced feature space, improving diversity in predictions, and possibly reducing computational complexity. Without PCA, ensemble methods combine predictions from different models trained on the original feature set. While effective, they does not leverage the potential efficiency and generalization improvements offered by dimensionality reduction. Comparison graph. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. In this project, we have utilized CIC IDS 2017 dataset with and without PCA. These are the graphs of CIC IDS 2017 dataset without PCA. This is the accuracy comparison graph. Here on the x-axis we have accuracy score and on the y-axis we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis we have precision score and on the y-axis we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. Here on the x-axis we have recall score and on the y-axis we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis we have FN score and on the y-axis we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. These are the comparison graphs of CIC IDS 2017 dataset with PCA. Models are compared with the parameters accuracy, precision, recall, and FN score. These are the comparison graphs of CIC IDS 2018 dataset without PCA. And these are the comparison graphs of CIC IDS 2018 dataset with PCA. So here we can see models are compared with the parameters accuracy, precision, recall, and FN score. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contains algorithm information which will be loaded into the project code during runtime. These are notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link. And paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created, and then click on sign in. We have logged in successfully. So here we need to enter all these parameters to predict whether threat is detected or not. So I'm entering the parameters now. So here I have entered all the parameters of the dataset CIC IDS 2017. The first parameter is flow duration, which is 640. The time duration taken for packets to flow between source and destination within the network flow. Total length of forwarded packets is 440. The overall size of forwarded packets within the flow. Forward packet length maximum is 220. The maximum size observed among forwarded packets. Forward packet length mean is 62. The average size of forwarded packets in the flow. Forward packet length standard deviation is 107. The standard deviation in sizes of forwarded packets within the flow. Flow bytes per second is 124. The rate of data flow in bytes per second. Flow packets per second is 171. The rate of packet flow per second. Flow IoT standard deviation is 135. The standard deviation of inter-arrival times within the flow. Flow IoT maximum is 445. The maximum value of inter-arrival times in the flow. Forwarded IoT maximum is 497. The maximum value of forward inter-arrival times. Forwarded header length is 164. The size of headers for forwarded packets. Forward packets per second is 1093. The rate of forwarded packets per second. Backward packets per second is 6250. The rate of backward packets per second. Maximum packet length is 220. The maximum length observed among individual packets. Packet length mean is 66. The average size of individual packets in the flow. Packet length standard deviation is 99. The standard deviation in sizes of individual packets within the flow. Packet length variance is 9801. The variance in sizes of individual packets in the flow. Average packet size is 72. The mean size of individual packets. Average forwarded segment size is 62. The average size of forwarded segments. Forward header length is 164. Another representation of the size of headers for forwarded packets. Subflow forward bytes is 440. The number of bytes within forward subflow. The initial window bytes forward is 8192. The initial window size for data transmission in the forward direction. Initial window bytes in backward direction is 2053. The initial window size for data transmission in the backward direction. So here we have entered all the parameters for the dataset CIC IDS 2017. After entering the parameters, click on Predict button. So here we can see we got the result. There is no attack detected and it is normal. Now we will enter another set of parameters for the dataset CIC IDS 2017. So here we can see we are doing the prediction using CIC IDS 2017. So now we will enter another set of parameters. So I'm entering the parameters now. So here I have entered another set of parameters for the dataset CIC IDS 2017. After entering all the parameters, click on Predict button. So here we can see we got the result. There is an attack detected. Attack type is DDoS. So in this way, by entering the parameters, we can predict whether attack is detected or not. Now we will do the prediction using another dataset. So namely CIC IDS 2018. So click on this. Now we will enter parameters for this dataset. So I'm entering the parameters now. So here I have entered all the parameters for the dataset CIC IDS 2018. So the first parameter is destination port, which is 3389, the port number of the destination device or system. Flow duration is 16658, the time taken for packets to transfers in a flow. Total length of forward packets is 1128. Total length of forwarded packets in the flow. Forward packet length maximum is 661. Maximum length of a single forwarded packet. Forward packet length mean is 141. Mean length of forwarded packets. Backward packet length mean is 225.8. Mean length of backward opposite direction packets. Backward packet length mean is 225.8. Flow IAT mean is 11899.07. Flow inter-arrival time mean, that is average time between two consecutive flows. Flow inter-arrival time maximum is 953123. Maximum time between two consecutive flows. Flow inter-arrival time total, that is total time between the first and last packet seen in a flow. Forward inter-arrival time mean is 2379. Mean time between two consecutive forwarded packets. Forward inter-arrival time maximum is 1117. That is maximum time between two consecutive forwarded packets. Forward header length is 172. Length of headers in forwarded packets. Forward packets per second is 4.8022. That is rate of forwarded packets per second. Backward packets per second is 4.20119. That is rate of backward packets per second. Maximum packet length is 1173. That is maximum length of any packet in the flow. Packet length mean is 169.31. That is the mean of the packet length. Packet length standard deviation is 137.73. That is standard deviation of packet lengths. Packet length variance is 1000953.16. Variance in packet lengths within the flow. Average packet size is 180.6. That is average size of all packets in the flow. Average forward segment size is 141. Average size of forwarded segments. Subflow forward bytes is 1128. That is bytes sent in the forward direction within a subflow. Subflow backward bytes is 1581. That is bytes sent in the backward direction within a subflow. These parameters play a significant role in analyzing network traffic within IoT systems for threat detection and performance enhancement in the mentioned project. After entering all these parameters, click on Predict button. So here we can see we got the result. There is no attack detected and it is normal. In this way, by entering the parameters, we can predict whether attack is detected or not. So here I'm entering another set of parameters. So here we have entered another set of parameters for the dataset CIC IDS 2018. After entering all the parameters, click on Predict button. So here we can see we got the result. There is an attack detected. Attack type is DDoS. So in this way, by entering the parameters, we can predict whether attack is detected or not. And if attack is detected, which type of attack is detected. Now click on Sign Out button here. Conclusion of the project. The model presented in the project, combining machine learning algorithms with principal component analysis techniques, demonstrated enhanced performance in detecting threats with an IoT system. The utilization of PCA contributed to a reduction in data dimensions, thereby improving the efficiency of processing and analysis. Consequently, this led to a reduction in training time while maintaining or even enhancing the model's accuracy in threat detection. The model's performance was evaluated using various metrics such as accuracy, precision, recall, and FN score. These metrics gauge different aspects of a model's predictive performance. The results indicated that the proposed model outperformed previous studies in terms of these evaluation metrics, showcasing its effectiveness in accurately detecting threats within IoT systems. PCA techniques are instrumental in reducing the dimensionality of the data. This reduction is advantageous for efficient processing and analysis of IoT system data. By retaining the most significant information while reducing noise and redundancy, PCA facilitated faster computations and enhanced the model's ability to identify crucial patterns within the data. The project utilized two specific data sets, namely CIC IDS 2017 and CIC IDS 2018, to evaluate and validate the proposed model's performance. These data sets likely contain diverse instances of IoT system data, which allowed for a comprehensive assessment of the model's capabilities across different scenarios and variations within the data. The project's intelligent approach significantly enhanced threat detection capabilities within IoT systems. By leveraging machine learning algorithms in conjunction with PCA techniques, the project not only improved the accuracy of threat detection but also reduced the time required for model training. This contribution represents a valuable advancement in the field, providing an efficient and effective solution for addressing security concerns in IoT environments.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.